Hello, this is Tom, and we're doing Unit 7. I apologize for the issues with sound and video today. I wasn't able to record this weekend for a number of reasons. And today I've been traveling with students. So I'm at a hotel in Minneapolis and don't have the best set up here, but we'll do the best we can. I'm going to share my screen and we're going to talk about Unit 7. Unit 7 gets into control structures. These are kind of the traditional building blocks of all programming languages: sequential statements, branch statements, and loop statements. We talk about them starting in CS principles and doing every course we've seen. Um, Now, both textbooks that I referenced in this field, of course, um, have a chapter on this. But the chapters tend to cover older methods of and traditional methods of sequencing that and leave out some of the newer methods. And so I'm covering some of the older stuff, but really focusing a lot more on some of the newer stuff. So we'll see that. So I'll skim over some stuff today. So we're going to start looking at sequencing. Uh, and the first thing, so the traditional sequence is just this, you do this statement, you do this statement, it's one statement after another, and you just go in order: step one, step two, step three, step four. That's how it works. And then again, Python, JavaScript, they all work the same way. Uh, Now there are a couple places where we will skip over. We won't do every part of every step, and that's usually with Boolean conditions. So let's talk about short circuiting. Here we have a variable, we set A equal to some value like true, B equal to some value like false, and then we have this Boolean result and we set it to A or B and some function call that probably returns a Boolean value also here. But this function will never actually get called here because again, we can see that A is true, and we have an or. So as soon as we see A is true, we know the result is going to be true. So we can just skip over the rest of this. So this is what's called a short circuit. These statements will never be executed as long as we can tell that A is true at this point. And that we have an or here, we don't have to execute those statements. But again, there are some cases like this where where the computer will skip over parts of it here. And again, we see this in all the languages: Java and JavaScript and Python. Every language has this sort of stuff generally, and we'll do some sort of short circuiting of this. Again, this isn't that common, but I just want to mention it here. Um, the next thing we want to talk about as far as when we skip sequences is error handling. And this is generally with our try catch blocks here. So let's just talk about the general idea of a try catch block. And again, I'm sure you've seen this somewhere before, hopefully. If not, well, here's the explanation. So if there's some code that might generate some sort of error here, we put it in a try block. So we take try and we start a block and end the block here. And then and then we do a catch and we list off the different exceptions, especially if we know there might be an exception we want to catch and do something with. So maybe we think this exception is okay in this case. We know how to handle it. We just have to do this or whatever. And that we don't, it's not really an error. It's something we know and we can expect. So we catch that exception and recover right from it here, there. So it's try, catch, and sometimes in catch we just raise a new error. We'll print a new error or raise a new exception here. And then again, you might a lot of times you'll catch individual exceptions, and then any exceptions you haven't caught will be listed under finally, and you have a finally here and list out what to do if it's not here. So like in this case, we'll do this code, and if arithmetic exception is generated, we'll do this code. If any other exception is generated, we'll do that code. And then once we've done these two lines of code, and if there's no error, we just skip over all that and go down here, right? So that's traditional try catch block here. And then I guess kind of walk you through this. Um, and again, most languages have something like this. Python has a try and except. So rather than catch, it's except and a finally here. So we can do that here. JavaScript has a try, catch, and finally. Now, often students, in beginning projects, we don't use this very much, but there'll be some places where we're calling something and the computer will require us to have it in a try catch. So that's where you may have run into it, is where you're forced to use it. But in a lot of projects, in business, they're more trying to catch errors and watching errors and that sort of stuff. So it might be more common to do try catch than you're used to doing in assignments and stuff like that. So again, and that's a place where, again, the order of things might not follow. Again, we will go here, here, here. And if these execute, okay, then we'll, again, it's almost like an if then statement. We'll jump down here, here. Or if there is an error, we'll jump to the corresponding state, and then we'll keep going down at the end. So just a different structure. It comes around similar to like a branch statement in some ways, but it's all structured on catching errors. Uh, um, so as long as we're talking about ways of getting in and out of code, that we bring up the topic of um, multiple returns or from a function or break statements out of a loop here. And this is one of these controversial things where lots of developers have strong opinions on them one way or the other. So the prompt here asks for different beliefs. And again, often this is codified in some sort of standard at different organizations here. So there are two main points of view. One is that we will allow multiple returns in functions. We can have multiple returns, and that's fine there. And the other one is you only have one return that's at the end of the function. You always have that. I believe older people like myself who were trained with go-tos and then trained to not use go-tos and always return at the end follow under this. At least that seems more familiar to me. Where this process seems to be a newer and again, in some ways, a little more concise idea here and multiple things. So again, here's our example from Java. We have a find value function here. And again, often what we're doing is doing some initial test check on it, and we're catching this if something's wrong. So if the array is null or the length is 0, we're just returning some error value right away for that. Otherwise, we're doing this, we're trying to find some value. If we find it, we return it right in here. And otherwise, we'll return something here at the end. So again, this has 3 different returns here. I know some coding standards will allow this sort of stuff where we have catching some uh, air conditions or things like that right away at the beginning, but then only have one return after that, and not would not have this here. But again, sometimes that's difficult. So again, and this shows it in Python and JavaScript here. So again, there's different arguments for this stuff. I'd be interested to hear if which of the do you prefer or see value in having anything? Do you see anything wrong with having multiple returns in a function? There, or does it seem that it can make sense to me? Similarly, break statements or continue statements in a loop. So again, we might have a loop and then we'll say break and get out of the loop here. And then again, we didn't ask about continue, but continue is also often here where you continue, where you just do the next, you jump down to the end of the loop and keep going. So break will break you out of the loop, right? And get you out of the loop, where continue will go down to the end of the loop, reevaluate this condition, and then see if it wants to continue in a loop or not there. And I was always taught that, good programmers don't need to write breaks and continues, that you don't need those. But again, there are some arguments as far as efficiency and clarity where breaks and continue statements do help with that. So yeah, I'm kind of interested to know what you're feeling on this. If it's just an old person way of doing it where we, for readability and maintainability, we say you should use breaks here. So all right, so let's go on to the next thing. The next thing is selection. So again, our branch sort of stuff, ideas. And so this is the classic if then statement. So again, this whole beginning thing is often covered in this. So stuff is the basic if structures and if then else or else if structures and nested if then structures. So, and again, when you might want to use an if then else if else structure, or when you use a nested where you have a whole if inside part of another if or inside the else clause and stuff like that. And again, I think we've seen that enough in different languages, and I find that all kind of boring, I guess. So I'm going to go over, kind of skim over that sort of stuff. And I want to look at some of the newer areas. Again, you're probably familiar with the switch with case statement, but there are some new ways of doing this with pattern matching. So let's talk about that. So traditional switch statement is in most languages, Java, C, JavaScript, all those things have a switch statement. And you always have to switch on some discrete value like integers or characters, and then you have a case for each one there um, for that. But now there are some, in a lot of languages, there are switch statements where you can do some more pattern matching here. So let's just talk about that. So in Java 17, switch with pattern matching was introduced. So here we have an object called hello. Again, this could be a string, it could be an integer, but again, it has to be wrapped or can't be well, it's certainly not a primitive type here. Um, and then again, we're doing this sort of a case statement where we're doing a switch on that object here. And then we have different cases for this. So here, the case, so this is a general object, and then if it's a string, S will do this. If it's integer, we'll do this. If it's null, we'll do this and do that. So we're actually uh, switching on it based on what type of object it is here. Um, and again, here's similar stuff in Kotlin where we're switching based on the type of this object and what it is here. So Rust is another language we haven't talked about much. I would say it's gaining popularity out there. There's some really strong advocates for it. I haven't used it much there, but again, it has similar functionality with its match value. So you can match some values. So you can look in that. So if you're interested in that, again, I haven't used this match stuff much, but so you might want to research it more as part of this assignment this week. So, all right. I'd forgotten to paste in the answer here, so or the response. So the next thing we want to look at is single line if statements, or what are sometimes called ternary operators or question mark operators in some languages there. So a single line if it can be written in a lot of languages, and we can just say like if in Java x is greater than 5, and then basically we're just not putting this on in the next line where often it is. And again, most coding standards want you to avoid that and want you to use braces for any sort of if-then structure like that. But again, we can write that same sort of stuff in JavaScript and more other ones here. Now let's look at the question mark operator from Java. So again, this is like an assignment statement there. So we're going to assign message some value, and we're going to base it on if this is true or false. So if this Boolean expression is true, when there's a question mark, then we're assigning it to the string to this value, and then we have a colon. Otherwise, we're doing this one. So again, it's trinary. So we have a Boolean expression, a question mark, and then the true value colon the false value here, and then the assignment will work that way. Um, and again, some people really like to use these, some people don't here. So again, in Python, we can kind of do this with, we can say message equals this, if this is true, else this, sort of writing JavaScript. Again, JavaScript has the same sort of question mark and colon values. So have you used this sort of stuff? Do you use these ternary operators? Do you like them? Or have you not used them, or have you seen them? So something to consider. Again, I know some, I don't use them, but I know some people who use them quite a bit. So okay, so we're going to switch. We were doing branch or um, selection statements. Now we're going to do iterations, the loops here. Um, well, again, the one thing I think you're probably familiar with is for each versus counter controlled loops. So you were taught counter controlled loops here for this. Um, and we're going to talk about for each. Oh, I see our problem here. I pasted in. This is actually the if then structure. Let me pause and fix this. Um, okay, so let's look at loops, particularly for each loops versus counter controlled loops. So again, you learn counter controlled loops initially for this. So this is a counter controlled loop, right? For int I equals 0, I less than or equal to like numbers dot length, the max value and I plus plus there, and then you're using this I to print out there. And the problem with this is that it is error prone uh, because you can make a number of mistakes in here, especially when you want to and often we just want to iterate over the whole thing, kind of like a boilerplate stuff. So again, we have our for each loop. Again, sometimes it says for each, sometimes like Java it says just for, and we say int numbers, a number in numbers, and then we print off that for that. And again, we can do the same thing. There's a for each, it's just a for loop in Python either way. And again, same with JavaScript for this. We can do this. So again, we generally want to prefer the for each kind of loop when we can. But there are a number of conditions where the for each loop it doesn't work. The for each loop basically works anytime you want to do something for every element in a array or a collection or something. Every element you're going to loop through and do that, which is a lot of times. But um, if you are needing to keep track of the index that you're at, what points you are at the spot, then you may need to keep track of that. So like here, we're keeping track of this index and we're actually referring it in two different arrays and managing them both here. If you're doing something in reverse, so we're going through this list in reverse order. Um, we're doing this, we're doing every other item in a list or something like that. Anytime we're not doing every single item in the list from top to bottom, that again, multiple lists or something like that. Again, there are actually some languages will let you do multiple for each iterations here, but like Java and stuff, this sort of stuff won't work. So you need to do a counter control. So there are a number of places you want to do counter controlled, right? But in general, you want to be avoiding those. So now, how do these counter controlled and these other loops work? Under them is something called an iterator. So I thought we'd try to talk. I don't know if you're familiar with iterators here, but we talk about what an iterator is and the idea here. And you can actually declare iterators in most languages and use them there. I'm not going to go into too much detail here, but I'll just talk about these things. So you can declare an object, an iterator, uh, here and give it the name, and they're just calling it the iterator for it. And again, so they have some list here, and they're just getting the iterator from the list here. And then you can ask things like iterator dot has next. Is there a next item in the list for that? So again, the for each loop has an implicit iterator that works through here. But sometimes if you want better control over this, you can use an iterator. So again, you can ask if it has a next value, and then you can say iterator dot next to get you a next item. Now here, iterator dot next will get you the next string because this is a list of strings. Sometimes iterators are their own type, and then you have to use some sort of special notation to, it's almost like a pointer type you have to do in some language, particularly in old C++ and stuff you have to do. So again, you can talk about this Python has the weird iterator, kind of under the hood operators you can do. And again, JavaScript has this sort of stuff. So again, I don't see them commonly use. I just thought we could mention iterators and talk about them a little bit because that's how these are implemented generally under the hood here. Now, the next thing I want to get into is loop, as far as loops go, is kind of map sort of stuff. Uh, I see this a lot in Python, but I also am seeing this move into more Java and other languages here for this. So let's talk about how this works. So again, map is a command that's where we're going to do some sort of standard transformation or operation on every element in a collection here with we're going to run a given function on every element in the list for this. Uh, Reduce, we'll do the same thing, run every element through a function. But again, we're reduce, we're uh, providing a single value as a result, so maybe like totaling it up or something like that. And again, filter is when we're going through every element in the list based on some condition and selecting some elements out of that list here. So map is running the same function on every element in the list. Reduce or fold, sometimes it's called, is running the same function on all the elements in the list, but we're combining them into a single thing, a single value often, like a total or something like that, or max. And again, filter is kind of slicing up a list and selecting items in this. And again, this is relatively new in Java. We use something called streams for this. I've talked about some alumni who are working in the field, and they say they use Java streams a lot in their real code here. So I think this would be a good thing to look at. So let's say we have a list of numbers here. So this is just a list of it, and we set this up. So these are our numbers in this list of numbers. So we're going to convert that list into a stream. So we just say list numbers.stream here. And then we're going to do a map. So again, map will apply this function to every element in the list. So every element in the list, we're going to get that number and take that number times two. So double every element in the list. So rather than 1, 2, 3, 4, 5, it'll be what, 2, 4, 6, 8, 10 here. And then to list, we'll convert it back from a stream to a list. Now here we're going from list to streams. Now a lot of places people I've talked to actually work a lot more with streams rather than lists. And so this conversion to a stream and back to a list won't happen. They'll just do a map because again, their data structure will just be streams for this here. So again, filter, we'll say, oh, I want to go through the list, and for every element in the list, I'm going to check if it's divisible by two. If we divide by two, if it's even, basically, when we divide by two, if there's a zero remainder. So if it's even, then we're going to add it. So this creates a new list here, and this is a filter here. And then we can also talk about reduce, where we're this is some initial value, and then we are for every value in our list, and we have some accumulator or something like that. We're adding this to the accumulator here. Uh, I have not worked with these very much here. Again, this is all new stuff before I did a lot of programming there. But again, a lot of alumni I know have done a lot, say that their companies use these streams a lot and we'll see code like this a lot in them. I'm interested to see if you've seen this and if you're looking at something to investigate in the assignment. I think this would be a really good thing to do. So again, Java has this all using streams for that. So I don't know if you're familiar with this. Again, Python has a lot of this built into their functions and methods. So again, we can do a lot of maps here. We can filter. So we can just say list.filter and then define some function here and apply this function to every element in this list here to just, so again, if we're just trying to grab all the even numbers out of the list, this is the Python way of doing it here. And again, reducing a list will, again, this is just summing up all the elements in the list for that stuff. So again, Python, I see this very commonly done in Python. I rarely see like things that I would think you'd have to do in a loop, like find the average or select every certain values above some value out of a list. Uh, I see a lot of Python code will use these sorts of values with it. Now, these are converted things to lists, but again, in Python, a lot of data structures are lists automatically. And again, when you deal with some of the bigger data structures, like I think it's NumPy has a lot of the stuff built into it also, which is a standard library in Python here. So JavaScript also has map, filter, and reduce on arrays that you can look at. So again, interested to see if you've seen these, if you see people using these a lot. I think these are becoming much more common, and we are not teaching them very much in our courses. So be interesting to know. Okay, so that's the last part of our loops here. So we're going to look at some so besides sequence, selection, or branches and loops. What other structures are there? So one thing that's really common is event-driven programming, and we actually use that. And we first actually teach that in CS principles. If you've had game design, or if you've had mobile app programming, you've seen this sort of stuff. So it's sometimes called event-driven programming, sometimes called reactive programming here. So again, rather than your traditional flow here, we are waiting for some event like a key click or a mouse click or sensor input or something happening. Maybe we're even sending some data out to the database and getting a response back, or any sort of asynchronous operation where it's coming back to us or like an API call to read some data in, we send it out, and then we have a listener waiting for to when that results here. So again, traditional control flow is very linear and sequential, and this event-driven program is determined by events. And so there usually is some sort of system control flow in here that's behind the scenes, and then we are declaring event handlers or something like that here. So again, we're talking about some examples of this. We certainly see this a lot in Android. We define event listeners and callbacks. So again, if you're doing some asynchronous operation, when that result comes back, like you're going out and grabbing data from an API, when that API returns with the data, it will call. You give it some function to call when that data returns from this. So, in game design, when if you we do C# with Unity, there's a built-in game cycle within the Unity game engine. And so for every method you can say do this at start or every update here. So every time the game engine updates something is an event. But then there's lots of trigger events like man, something is pushed or a key happens or something like that. You can check some conditions like that here. And again, in web design, you see this a lot with event handlers and JavaScript. It's kind of event-driven programs. So if you have a form and you have some button or whatever, you're defining listener or what kind of methods you want happening with certain events here. So again, just kind of familiar with this. We're going to look at a couple examples of it. So um, let's try to look at some actual examples in this next one. So again, this is JavaScript event listener stuff. So again, we have a button on a website. So we've got the button there. We're going to define a handle click that we want for that button here. So then with the button, we're going to add an event listener with a click event, and then we're going to specify that this function will be called. So that's pretty traditional handle button click. And again, you'll see this. We see the same thing in Android development for mobile apps and stuff like that, where you're defining listeners, event listeners, or something like that for events like mouse clicks on certain items in your user interface here. Um, okay, so the next thing I want to get into is recursion. And again, this is uh, one of these things where I think some universities teach it a lot, but to tell you the truth, I don't think it's actually used much in the real world. I know very little real world software that uses recursion. So we'll just talk about it. There are some places where it is kind of useful here. So the typical example of recursion is, again, a recursion is when you have a function call itself there. So a function calling itself there. Now, in general, if a function calls itself, you'll get an infinite loop. So you generally break your code down into two things: a base case where you're handling it and where you're not recurring. We don't have recursion, and a recursive case where, okay, if it's not the base case, then we're doing the recursive case and we're calling it up. So the classic example is factorial. We know that n 0 factorial is 1. So if n is 0, we can just return 1. Otherwise, uh, and so that's our base case. And otherwise, we do our recursive case where we return n times the factorial of n minus 1. And so this is calling this factorial with n minus 1 recursive. This, and I'll keep calling it until n is 0, and we'll get a 1 back. And then the recursion will kind of unwind. And again, we can do recursion in all these languages. Every language almost, I think, supports recursion. And again, if you have trouble understanding recursion, you might want to walk through this. But again, I think you probably have seen recursion before. There's something called tail recursion, where again, we're working through a list and we're often popping or working, doing something on the last item in a list, and then kind of popping it off the list. And so you can almost anything you do with iteration with a loop, you can actually do with tail recursions. And some people are a big fan of tail recursions, especially in some areas. We'll get to functional languages that don't have loops. And so in those sorts of languages, everything has to be done with recursion. But again, those are not that common in real world applications here. So you can walk through this. And again, I'm not going to do too much, but I'm going to leave this. If you're interested in recursion, you can deal more, you can explore this more. The third type, kind of, well, my idea of third class of recursion is the divide and conquer. Again, where you can have some problem, you can divide it into smaller parts. Like I always think sorting is a good example here. So a lot of the more complicated sort algorithms will work with this. So like the merge sort will take a whole array, divide it in half, sort each half recursively, and then you will call merge sort on each half of the array and break it down and find. So you might have some big list. You're going to break it down into smaller lists, break that down into smaller lists, and again, you're either going to stop when you just have two items in the list and you can compare them, or you're going to even go down to where we have one item in the list and then you can just return what is the largest one when you just have one item. It's easy. It's that item here for this. So again, and there's this sort of divide and conquer. So similarly related to this, I think, is the fact that there are some data structures that work better with recursion there. So especially stuff that does not have a linear or a grid-like structure to it. So certainly trees and binary trees and there's and linked lists and graphs. So again, here they're showing examples of trees. So like in order, pre-order, or post-order tree traversal, and I think you cover all those in the data structures course, and for linked lists there. So again, this sort of stuff where you will call a function on some item, you'll do some base case, and then you'll do something to the rest of the list here. And again, this works really well with recursion. Some of items like this, and again, this sort of searching a list with in order or pre-order or post-order sort of stuff. Similar to exploring a graph, there's some good. So there are some places where working with recursion really well works well. And another area that, well, a couple areas here is just nested structures where you can have a object within an object like JSON or XML, where you can have items within items and stuff like that, and you want to just do something and explore that whole object. You don't know how deep it goes or anything like that. Recursion will help with that. So again, there are some places where recursion is very useful. Okay, I think we're getting near the end here. And again, think of what items you might want to explore as the assignment this week. So asynchronous functions are the last thing I want to deal with here. So again, there are times where particularly you will want to do this. So in a normal sequential thing, there's just one kind of thread of control, and we're going line by line by line. And sometimes we're branching, and sometimes looping. But again, there's just one thread of control that we're controlling. But sometimes we'll need multiple threads, or we'll need some sort of asynchronous function here. So a lot of this has to do with things that are we call blocking. So if you have a UI page and you're going out to get something or read something in, and you don't want your screen to freeze while you're doing this other thing. So you want to keep responsiveness in your UI. But again, you're getting data from some remote site, or you're reading data from the drive or something. Any of those things that going to take lots of time compared to UI functionality here. So responsiveness certainly, there are some times where we want to do multiple things at the same time, and sometimes from a performance point of view, you want to be running multiple things at the same time. So I'm going to skip over this because we actually talk about this, I think, later. Oh, let's see. Oh no, I do want to talk about the traditional one here. Okay, so the traditional approach to threads uh, talks about creating threads manually, locking them, and using something called a semaphore to control access in and out of a thread for this. I'm not going to deal too much with this. You should not be doing this anymore here. And then we get to an issue called deadlocks, and there's lots of people who like to study deadlocks. But again, a lot of this is not, you will never have to deal with it in your code program. So again, they talk about creating a thread here, and you can lock that some counter variable so that no one else can use it, and then you can work with it, and you can unlock it later on and work with it. And again, this isn't even showing how you create the thread and spin up multiple threads here. This is just showing how you might use lock and not. So I don't think that's the best example, but that's what we have. But again, I would suggest you should never, unless some special case, you should never be using old style threads without some nice library around it. So let's look at what the traditional libraries are. So the most common one is an async await kind of pattern here. And again, we see this in multiple languages where we'll if we want to call something here, we can call it, and we can call await here, and call await and call await, and we can do more stuff while this is being processed here. You can try these things and catch some errors for this and doing things. So an await keyword generally can only be used inside the async function. So often when you start making things asynchronous, you put these awaits in here, but then you are required to make the function asynchronous in most languages like JavaScript here. And again, await will pause the execution until this function returns, until this value returns. So other parts of your code might be working, but this part will be waiting here. So your UI might still be operating, but this part we'll be waiting for this to run here. Python has a library. One of the common ones is async.io here with a similar await structure and an asynchronous function for this. C sharp has a similar thing, and we see that sort of stuff. So again, we can use awaits here, and we make an asynchronous, and we actually have an asynchronous task here. So rather than declaring this as a string, so this fetch thing is not returning a string, it's returning a task string. And this is like you'll see this often described now as a future string or a promise string. In C sharp, it's called a task, meaning we can access it now. But later on, we can get access to it after we await or after it's done. We'll call this method here. It'll go do some stuff. We'll return a task string, and then we'll await that, and eventually that task string will become a string, and then we'll do this assignment here for this. So now we thought one of these talked about the promise structures. Okay, well, let's get into, so again, this is a number of languages, but not Java. You notice we didn't mention Java here. We'll have this await async pattern, which we see fairly common. And then Java and now Kotlin. Java introduces a library, kind of, I would call it a library called Loom for this. And so here we can create tasks, and we are starting to return what is called a future object here. So rather than a string, this is a future string. So in the future, it will be a string for this. And this code will, this is actually what's called structured concurrency. So there's some structure around this. Let's see right there at the try part. Um, So we'll create a structured task scope, and we'll define certain futures within that. And then we can also join these futures together within the scope. But what that is doing is saying that we will wait here until these futures are all done. So you can set up a lot of things to run, and then we'll wait here. So now. Again, now we're calling result now here from result one. And again, that should be going up to this result one. And again, this, it will be a future for a while until here, and then it'll wait here, allow other processes to work. And then now after that, we can get the results by calling this result null sort of idea. Um, So again, that's one thing. I have not used Loom that much here. I've used the C sharp stuff more. Kotlin has a similar stuff here with this, and they have a deferred sort of object there. Again, I'm seeing this more and more where we're seeing a promise or a future object or a task object here. So we're not dealing with um, a string. Here we're doing with the task string, or I should have brought, I think, React in JavaScript, and I think maybe it's all of Node .js has tasks built in. I believe that uses let's see, a promise of one, not a future of one. So again, there's different techniques of that. But again, this is an area I think if you haven't familiar with, you might want to explore some more this week. So the last thing I just want to talk about is when we're dealing with async, we talk about threads generally, and it's easy to confuse processes with threads with like microservices or what a service is. So we just want to talk about those a little bit here. So a thread is a small part of a process. Every process can have multiple threads running. Each thread, will be a separate thread of execution, but they're all in one process, so they're generally running on one core or one CPU there. A process is an instance of a program that's running in its own memory space and stuff. And so processes can, if you have multiple processes, they can be running on multiple cores there. And microservices is where we're spreading this out into more of a structural issue where we're trying to define a large framework and build things around that here. So again, when do you want to use threads? That's when you have parts of your computer or program that are going to kind of hold up or pause there, or there's some concurrency issues. When if you want to be running on multiple cores or CPU things, then you're going to be working with multiple processes. And again, if you're just trying to break a large system up into smaller processes, you're working more with services and microservices. Okay, sorry this was so long today. Hopefully it was okay.